Okay, so this is a review of chapter 3 and 4, just some of the major topics that we have covered, just to give you a little bit extra practice outside the classroom if you feel like you still need it. So first thing in chapter 3 we talked about in leading into bonding is figuring out valence electrons. So do remember that the way to find the valence electrons is to look at the group number at the top of each column. So I've got, this one's a little different than what yours looks like, but you see that group number 1A, 2A, 3A, 4, 5, 6, 7A. It's the number in front of that capital A across the top for the first two columns and the last two columns, the main group elements that you can use to determine the valence electron number. So you really don't have to be able to sit down and write out electron configurations or anything like that. So in this, sodium, notice it's in group 1, so it would just have a single dot. Nitrogen, being in group 5, is going to have 5 dots around it. Hydrogen, 1 dot. Magnesium would have 2. Argon would have 8. So argon's all the way in the far right corner, or far right column, and has a full set. Sulfur, 6. Carbon, 4. Chlorine has 7 in group 7A. So in this, you're just going to leave 1 won't be paired. Sulfur will have 2 that are not paired. Carbon will have 4 that are not paired. Aluminum has 3. Oxygen, 6A is its group. Fluorine is in group 7. And notice it really doesn't matter the way that you put them around. You're just putting them surrounding the symbol. Always just keep 2 up, 2 to the right, 2 to the left, and 2 down as a maximum, 2 on any side, and just based on the number from that group number. So with phosphorus, it really doesn't matter where you put the double pair, the 2 electrons. You can put it on the top or the side or the bottom. That really doesn't matter as long as you have 5. And a general rule of thumb is if there's just 1, I just put 1. If there's 2, I often pair them like you see with magnesium. But once I get to 3 or more, I begin to spread them out and only pair them up when I have more than 4. I think that it helps you to see that there's like an empty spot here. You can kind of see that there are 3 here that are not paired. That especially comes in helpful when you're thinking about covalent bonding. Okay? So now we went through ionic and covalent bonding. And so in each case, you should be able to look at a molecule and tell me if it's an ionic or a covalent molecule. The rule is if there's a metal first, then it's ionic. So as you look down through this, you see CAN, you see that it's ionic. Calcium is a metal. Remember that metals are to the left side of the zigzag line. Iron, ionic. Magnesium, ionic. NH4, remember that this is the exception. And when you look, you're like nitrogen, well, that's a nonmetal. But NH4 is the ammonium ion. So this is an ionic compound. Copper, ionic. Potassium, ionic. Aluminum, ionic. So all of the elements except for that one exception, ionic because the metal is first in the list. So whether you're looking at a name or if you're looking at a formula, that's really all you have to look for. So in this, remember that the formula tells you the number of each, and it's always a defined number. You don't have to use number prefixes with these. You just use the whole name of the metal, first part of the nonmetal, plus IDE. So this is calcium nitride. Now, iron, chromium, and copper, Fe, Cu, and Cr. Remember that they are the transition metals that need to have a Roman numeral because they can exist as multiple plus ionic stages. And so you always have to figure out what the charge is. So like from this one in the formula, if I do a reverse swap, telling me that the phosphorus, 2 phosphorus tells me the charge on the iron, 3 iron tells me the charge on the phosphorus. This Works most of the time unless we have a simplified molecule. So my suggestion is always go back and check the nonmetal charge. If the nonmetal charge matches the charge based on what the periodic table tells you, so for example, phosphorus has 5 electrons, so it is going to end up with a -3 charge. So that matches what I say it would be based on swapping the formula to figure out the charge. So that tells me for sure that this is a +2 for the iron. Because remember, iron can exist as a +2 or +3. That is why you put the Roman numeral 2 in front of the iron, and the phosphorus becomes a phosphide. When you see a metal and then a group, remember that when you have those nonmetals with a bunch of oxygens, those are polyatomics. So you don't name the sulfur and the oxygen individually. SO4, 2- is the sulfate. Whole name of the metal. And then the polyatomic name, magnesium sulfate. NH4F, NH4, remember, is the ammonium ion, so you use just the name of the ion. When you have a polyatomic, you just use the name of the polyatomic, but then the F becomes the fluoride. So this is ammonium fluoride. Copper 2 nitride. So with these last 3, we're going from names to formula. So just put down the name, the symbol for each one. So that means I know I have a Cu. Sorry, that looks kind of weird. I have a Cu and I have an N. Copper 2 tells me that I have a +2. So the Roman numeral 2 tells me the charge. Just like up here with the iron, the charge is why I put that Roman numeral in front. Nitrogen is a -3. Right? So nitrogen has 5 electrons. It's going to gain 3 in order to make 8. So it's got a -3 charge. So here, just swap them. So copper becomes a 3. Nitrogen becomes a 2. The charge on the metal tells you the number of nonmetal atoms. The charge on the nonmetal tells you the number of metal atoms. Potassium sulfide. Potassium is K and has a positive charge. Sulfide is sulfur and it has a -2 charge. So in this, you have to figure out, okay, looks strange. In this, you have to figure out what the ratio is. Swap the charge on the sulfur, tells you that there's 2 potassiums. The charge on the potassium tells you that there's 1 sulfur. That just looks worse. Sorry. There. Okay, K2S. Can't simplify it anymore. Aluminum carbonate. Aluminum is Al. I have a +3 charge. Carbonate is CO3, 2-. So remember that the carbonate, not carbide, but carbonate, is a polyatomic ion. So swap them. But now the difference is remember this 3 means that I have 3 CO3s. So I keep the Al. I've got 2 of them based on the carbonate charge. But the CO3 is going to have the parentheses. Okay, so make sure that you go back over the polyatomics as well as the transition. So this page is a combination of ionic and covalent molecules. The first thing to make sure you do is identify if it's ionic or covalent, and then give the correct formula or name. So after we've talked about the last page, if you're feeling confident, I would say pause this, work them out yourself, and then listen for the answers. So the first one, copper 2 oxide. So you look at copper, you see that it's a metal, and that is going to tell you that it's for sure, it's ionic. S2Cl5, so you look sulfur to the right side of the zigzag line, so you know that this is covalent. Aluminum fluoride, aluminum is a metal, so you see that it's ionic. Carbon is a nonmetal, so that is covalent. Nitrogen is a nonmetal, that is covalent. Iron is a metal, so that is ionic. Ammonium is the polyatomic, so remember that would make it ionic. Tetraphosphorus, so phosphorus is a nonmetal, it's covalent. So first identify which. Remember with ionic, you just either give you have to figure out the formula, or you would just write first name of the nonmetal plus the, whole name of the metal, first part of the nonmetal plus IDE in the naming, but otherwise you're going to have to figure out the formula based on the charge. So in this one, copper 2 oxide, remember that copper, chromium, and iron are the ones with the Roman numerals, so that one needs to have a copper 2, tells you that it's Cu and it's a +2. Remember that oxygen is O and it's a -2. Okay, oxygen is a group 6, so it's a -2 charge. So here we're going to swap, but now notice when we swap, you would end up with Cu2O2, and you always want to make sure you simplify ionic compounds if you can. So their simplest ratio would actually be just CuO. S2Cl5 covalent, so this means you have to use number prefixes. So ionic does not use number prefixes, covalent does. So this would be disulfur. 5 would be penta. 2 sulfurs, 5 chlorines in that one. Covalent, use the number prefixes. Aluminum fluoride, we said, is ionic, so we don't need number prefixes. We're just going to write down aluminum, and that's a +3. Aluminum's in group 3. Fluorine is an F and has a negative charge. So to figure out the ratio, you do the swap. So aluminum will just be 1, but the fluorine, you'll have 3 of them. So AlF3. C2O3, so this is covalent, so that means that I have dicarbon trioxide. NO4 is covalent, so if you only have one of the first element, you don't have to put mono, you just write its name. So this is nitrogen, it's tetra oxide, so it's tetroxide. FeSO4, so with this one, remember that with iron, you're going to have to figure out, if you look on the periodic table, it's a transition metal. Remember, it can be +2 or +3. So you've got to figure out which one it is. The best plan, look at the nonmetal. This is the polyatomic. The sulfate is a -2. So since it's a 1-to-1 ratio, that tells me that it has to have a +2. And so that means that this is iron 2 sulfate. So in this one, I need to figure out the charges so that I can figure out what the correct Roman numeral would be. Whereas ammonium hydroxide, ammonium is NH4+. The hydroxide is another polyatomic. So here I have 2 polyatomic stuck together. And this, notice that it's a 1-to-1, so it would just be as it is, NH4OH. So don't connect those hydrogens, so you wouldn't write it out as NOH5 or NH5O, because polyatomics exist as kind of individual groups. So just list this polyatomic formula and this polyatomic formula. You don't need to put those together or condense them. Tetraphosphorus trisulfide. This is a covalent molecule, so tetraphosphorus tells me that I have 4 phosphoruses, and trisulfide means that I have 3 sulfurs. So I hope that helps in terms of the naming. It's really just a matter of first determining, do I have ionic or do I have covalent? And then whether you need to know formulas or if you need to know names for them. All right, so once we finished covalent and about the naming, then we went on and start talking about shapes, because shape is important when thinking about the polarity of covalent molecules. So the first one, and really just stick to the examples that I gave you. I'm not going to give you large structures and ask you about shapes with them. I'm really going to stick to very similar molecules to the ones we did as examples. So in the first one, remember that we have CH4, and this is the carbon with 4 single bonds. Carbon with 4 single bonds, if carbon is the central atom, it has 4 groups connected to it, and it has no non-bonding pairs. So that is the AB4, and that is always going to have a tetrahedral shape. While nitrogen with 3 hydrogens, remember that nitrogen is 5 valence electrons, so it forms a single covalent bond with each of those nitrogen, or each of the hydrogens. So when you look at this, if nitrogen is A, it has 3 groups connected, and it has 1 pair of non-bonding electrons. This is going to create that negativeness at the top and push those hydrogens down, and it creates a shape that is called pyramidal. Water, the oxygen, has 2 non-bonding electron pairs, and it's going to then, if oxygen's A, there's 2 groups connected to it and 2 groups of non-bonding electrons. Remember, non-bonding electrons create a repulsion or a push on the bonding pairs and actually push them so that the hydrogens end up being closer together than they would when you're comparing the hydrogens of CH4. This is going to create a molecule that is always going to look bent. So that's why you always kind of see water molecules having a bend to them. Carbon dioxide, with this one, you have carbon in the center, and it forms a double bond between each carbon and oxygen, between the carbon and each oxygen. But this is going to be a bonding group and a bonding group, so this would be an AB2. No non-bonding pairs on the carbon. Remember, when you're looking at non-bonding pairs, up here, the number of non-bonding pairs is always based on what the central atom is. So it's not the fact that those oxygens have non-bonding pairs, it's just that carbon you're comparing. And this, because of the fact there's only 2 groups, they get as far apart as possible, and that's going to give you a very linear arrangement. So those are really 4 of the 5, the last one being the trigonal pyramidal. So do make sure that you go back and look at those. So what I'd like you to do is draw these out or figure out the geometry with them, and then identify them as being polar or non-polar. So remember that polar, you're looking for nitrogen, oxygen, fluorine, or a chlorine. If there's just one, you're looking at polar. If there's more than one, you have to compare their appearance in the geometry aspect of the molecule to figure out, are they all on one side of the molecule or are they evenly distributed? Polar is when you have an uneven arrangement of these 4. Non-polar is when you either have none of them or you have an even arrangement of them. So if you would, you can pause, draw these 4 molecules, and then see if you do this right. Okay, carbon tetrachloride, yes, there's a chlorine. That is going to pull electrons this way, this way, this way, and that way. But do you see that that is an even arrangement? So this is a non-polar molecule. Has that tetrahedral shape. And so envision sort of the tetrahedral arrangement, but the chlorines are all pulling electrons to kind of create an even balance of those individual polar bonds. Here. So in this one, CH2O, this is a trigonal planar. So remember that that carbon is like in the same plane as the oxygen and the hydrogens, and it kind of ends up looking like a little triangle sort of shape, flat on the table. So this one, seeing this one oxygen, electrons get pulled this way. This side becomes more negative. Over here then becomes more positive, and that is a polar molecule. So notice in this one with CCl4, I have electronegatives, but they balance each other. Here, oxygen's on this side, and I could literally like split this molecule and say, okay, the electronegatives over on one side, and that creates the polarity. Carbon dioxide, we just drew in the previous page. Remember that this is going to end up with a linear shape. So yes, electrons get pulled towards each oxygen because each one of them is electronegative, but do you see that they balance each other? So this is a nonpolar molecule. NH3, the pyramidal arrangement, and if you really want to think about the pyramid, it really kind of looks like this. So that electronegative cloud at the top pushes the nitrogens further down. So can you see that that means that all of these bonds get pulled this direction towards the electronegative nitrogen. This side becomes more negative, this side becomes more positive. So this is a polar molecule. Just good sort of examples of ones that we've drawn in geometry and ones that have polar versus non-polar characteristics, so you can have them for comparison. Okay, so then the last thing about chapter 3 was moles and grams. Okay, so moles and grams you need to, and molecules, that was sort of the last, and that's the way that you kind of count in chemistry when talking about molecules. So remember that if you see moles and you see grams, you're going to need the formula mass. It's just a single step conversion. The formula mass is where you take the mass of each of the atoms in the formula and add them up. So hydrogen, round to the nearest whole number. That's our easiest way to do it. So if you look on the periodic table, remember that on the periodic table, this one's really hard to see. So if we look at the periodic table, you can actually see that the mass, their mass is not where it's supposed to be. Their mass is, they have extremely long numbers. I just found this one online. So this is 1.00794. Just take the 1. So just look on your periodic table. It's always going to be the number on the bottom. Take the number with all the decimals, round to the nearest whole number, and then just add those values up. So hydrogen is 1, and I have 2 of them. So that's a mass of 2. Sulfur has a mass of 32. Oxygen has a mass of 16, but I've got 4 of them. So that's where I get 64. So when I add all of those up, I get 98 grams per mole. So I know how many grams in 1 mole, so I want to know how many in 1.5. So 1.5 moles times in your line. So mole will go on the bottom and grams goes on the top. So see, it's just a single unit conversion. The unit I start with goes on the bottom. The unit I want to go to goes on the top. 98 grams in 1 mole. So then just doing the math. So doing the math, 1.5 times 98, and I get 147. Now, if I'm going to go by significant figures, 1.5 moles would round this up to 150 grams. If I'm going the opposite direction from grams to moles, then I'm just going to set it up. I'm just going to flip the unit of grams per mole, so it'll be moles per gram. So put down the unit you're given, times in a line. Grams then goes on the bottom, moles will go on the top. Just a single unit conversion. I'm going to use the formula mass, and I'm setting it up in this direction so that I can have grams and grams cancel and moles show up. So I end up with 0.510204082 moles. That's the number on the calculator, but I clearly can't keep that. 50 has one significant figure, so I would round that to 0.5. Remember, the 0 out front is not significant, so the first one I keep is that 5, but you do have to keep the 0 out front because it holds the decimal place. So the last one, if you see moles and molecules, then remember, you get to use Avogadro's number. And the only challenge really with this is making sure you can put it in your calculator. So Avogadro found out that there was 6.02 times 10 to the 23rd molecules in 1 mole. And it doesn't matter if you're talking about moles of water, moles of H2SO4, moles of carbon dioxide, moles of sugar, moles of air, whatever. It's just 6.02 times 10 to the 23rd molecules per mole. So in this, 1.5 moles. Again, it's just a single unit conversion. The unit you start with goes on the bottom. The unit you're going to goes on the top. So 6.02 times 10 to the 23rd per 1. Now in this, putting it in your calculator, if you're using a graphing calculator, do make sure that you use parentheses. That's going to make sure that that exponent stays together. If you're using the old school calculators, you can use the EE button and you don't have to use a parentheses in your value. So I got 9.03 times 10 to the 23rd. If you have problems trying, I apologize for my exponents looking so ridiculous, 23. Okay, if you have problems doing this, please come and see me. Please go and see one of the tutors so that we can go over it and make sure that you know how to do this part, just because you don't need to miss this. It's not necessary. Look at this though, 1.5. I've got to keep the 9.0 and I'm going to drop the 3. So I wouldn't drop it just to 9 to keep the number of significant figures. I would say 9.0 times 10 to the 23rd molecules in that sample. Okay, so just double check those, your given number. Remember the measured number. You don't round according to Avogadro's number. You don't round according to formula mass. Always go back to the measured number in your problem. All right, so once we got done that, then we went on to chapter 4. So chapter 4, the whole first half really is naming. It's naming, and then we went on to isomers, and then we finished up with chiral carbons. And so in that first one in naming, remember that there's the 4 rules. We have 4 rules with naming them. We have 4 rules when drawing. So in the 4 rules with naming, you always find the longest carbon chain. So I see one here, 1, 2, 3, 4, 5, 6, 7. I see one here, 1, 2, 3, 4, 5, 6, 7. So it doesn't really matter, should just pick one, okay? Longest carbon chain, 7, makes this a heptane. Then I've got to name this, I've got to name this, and I've got to name this. All of these are hanging off of the longest carbon chain. So if it's a halogen, you use the name of it. Look, I almost wrote flower. In the O, fluoro. This one, methyl. This one, ethyl. Find the longest carbon chain, identify each of the non-hydrogen hanging groups, number the chain. If I number from the left, my first branch is on 2. If I number from the right, my first branch is on 3. So that is why I will number from this side. So this is going to be a 2-fluoro, a 3-methyl, and a 5-ethyl. Last step is to list all of those groups, but you list them alphabetically. So in this case, I end up putting 5-ethyl first. Then I put a 2-fluoro, and then finally I put the 3-methyl. So the numbering pattern is not the criteria. You want to put it according to alphabetical. Okay, so look at these last 2. You can pause this, work through them. I'm just going to run through them and do the naming next. All right, so for this one, when you have a ring structure, the last name is the ring. So 1, 2, 3, 4, 5, 6. So this is a cyclohexane. This group is a methyl group. This group is a methyl group. So I know that I have a dimethyl. I got a number. So you're always going to start on one of the non-hydrogen groups. If you only have one, then that's the only one you need. But in this one, notice if I go this way, if I go 1, 2, 3, that will give me the lowest number pattern. If I go 1, 2, 3, 4, 5, that would be higher. So this will be my 3. This will be my 1. So I have 1, 3, dimethyl cyclohexane. The last thing you might notice, you notice the wedges. So remember with the wedges, that is telling you that those are both pointing forward. So remember that this is cis. So if you have 2 wedges or 2 dashes, that shows that the non-hydrogen groups are on the same side, and that's the cis conformation. This one, counting down, longest carbon chain looks to be the one straight down. 1, 2, 3, 4, 5, 6, 7, 8. So that makes this an octane. That's the last name that goes down first. Then just list each of these groups that are hanging off. So I have a methyl, I have an ethyl, and I have a bromo. Methyl, ethyl, and a bromo. Start numbering. If I number from the top, my first branch is on a 3. If I number from the bottom, though, my first branch is on a 1. So clearly, that's going to be the one that I want to use. 6, 7, and 8. So this is going to become a 4, and this is going to become a 6. Last step, list them in order. So in this one, their order and their numbering is the same, but it's not the numbering that determines it. You always list them alphabetically. Okay, 1 bromo, 4 ethyl, 6 methyl, octane. When drawing steps, go to the very last word. Very last part of the name tells you how many carbons to put down. Well, this one says cyclopentane. So as soon as you see cyclo, you know that you have to do a chain. Okay, there's a cyclopentane. And I want to do 1,3-dichloro. So you can pick wherever you want to put these, and I want them in a cis. So that means that I want to put, I'm just going to make this my first carbon, so I can make this one my third, and I'll have room for them. If they're cis, if they're cis, I could do them like this, off of carbon 1 and carbon 3. Remember that 2 dashes would be cis because they're both pointing backwards. 2 wedges would be cis, both pointing forward. And that's it. All the rest of those are hydrogen, right? So remember, these would be hydrogen. There'd be 1 more hydrogen on that carbon. There'd be 2 on this carbon, and there'd be 1 there. If you just did the skeletal structure, you would just draw a pentagon, and you could do them with the wedges, or you could do them with dashes. Wouldn't matter which one you did, but it would look kind of like that. Trans 1,2-dimethyl cyclohexane. So now I'm going to do something that hopefully looks like a ring of 6. I have 1,2-dimethyl, so I need to put 2 methyls on 1 and 2 carbons. So I'm just going to pick 2 adjacent carbons, and they're trans, so that means that 1 sticks out and 1 points back. So an indication of them, make sure that you use the wedge and dash if you see cis and trans. So that would be hydrogen, these would be hydrogen, these would be hydrogens. So if you look, you should count that there should be 4 bonds with each carbon. All the ones that I have empty spots, those will all be hydrogens. So now you stop, you draw these. See if you can draw these. If you run into problems, I'm going to work through them right now. First name, hexane. 1, 2, 3, 4, 5, 6. 6 of them, and then I have a 3-ethyl. So that means that I have a CH2, CH3 sticking off. You could expand this. You could draw them all with all the dashes, including this carbon having dashes and this carbon having 3 dashes connected off of, as long as it's off of that 3rd carbon. It would also be fine if you did it so that you put it off of this one, right? So you can see that the way I drew it right there and the way that I drew it before, remember that all the rest of these would all be hydrogens. 3 hydrogens on the end carbons, 2 hydrogens on all the other carbons except for this one, because it's got an ethyl group, it only has 1 carbon up. If you did a skeletal, you would do 5 lines. 1, 2, 3, 4, 5, 6 dots, like 6 corners or ends in this one, and then off of this middle one you would need to do a bend, because an ethyl is a 2 carbon group, so it would need to have a line coming down and then a bend in another line. 1 bromo 3 iodo cyclopentane. Good grief. Okay, cyclopentane. See, now this one turned out a lot more like a house, but just still the same idea. So 5 cyclopentane, 1 bromo, you just pick. So 1's going to be on a bromine, and then 2 more. So this is carbon 1, 2, and 3. And so this would be an iodo. So notice in this one, I haven't actually determined or said cis and trans. So if I don't, then just use just regular Lewis structure. These would be hydrogens. All the carbons have to have 4 covalent bonds. So if you count them now, you should see that there's 4 lines coming off of every single carbon. I'm just not putting them in. Sorry. 1,2-dichloropropane. So propane, 3 carbons. 1,2-dichloro. So that's a chlorine on carbon 1, chlorine on carbon 2. Do note that it would be fine if you wrote it this way, or if you put it so that the chlorines look like one was up and 1 was down. As long as you have 3 carbons and a chlorine off of one of the end carbons and a chlorine off of the middle, that would be 1,2-dichloropropane. All of these are hydrogens. So if you wanted to go back and add those in, you would have hydrogens on all of those empty spots. Now, getting into the pairs. So in this, I drew these 4, and I apologize, you'll have to go back and look at them again. Questions are the following pairs conformational isomers, structural isomers, stereoisomers, enantiomers, or are they not related? Okay, so remember to figure out if they're not related, you count the number of carbons. If they have different numbers of carbons, then just say they're not related and move on. If one has a fluorine and one has a chlorine, then you say they're not related and you move on. So you really do first have to compare the formula. If they have the same number of atoms, then there's some type of isomer. So then you've got to figure out which one. Remember that conformational isomers are the same molecule. They have the same name. So that's really the big kicker. Structural isomers have different names and different bonding. Stereoisomers have the same bonding, but they have a different spatial arrangements. You're going to see these with a ring. So remember that stereoisomers are going to have wedges and dashes, and enantiomers are going to have a chiral carbon. And you are going to have the mirror image of the chiral carbon. That's really the way to tell those four apart. So looking at the first one, I'm like, well, carbon and carbon, chlorine and chlorine, and 3 hydrogens. Okay, so they have definitely isomers, so they're definitely related. If I name this would be chloromethane, chloromethane. Both chloromethane, do you see that? It's just a single carbon group, so it's a methane. 1 chlorine hanging off. They're both chloromethane, so that means that these are conformational isomers. Okay, one underneath. 1, 2, 3, 4 carbons and 1 chlorine. 1, 2, 3, 4 carbons and 1 chlorine. Oh, so that means yes, they are related. They are isomers. And so in naming, this is 1 chloro, not a bromo. This is 1 chlorobutane. This one, on the other hand, remember when you circle your longest carbon chain, include non-hydrogen groups hanging off. So you really want to circle it this way. If you circle it this way, do you notice the chlorine's not attached to the chain? You want to make sure that the non-hydrogen groups are attached to the chain. So this is a propane. So I already know that this is not, they have the same number of atoms. They're put together differently. So I know they're structural isomers. Because they have different names. Going up into the top, looking at the ring of 5, 1, 2, 3, 4, 5. This is a cyclopentane. 1, 2, 3, 4, 5, 6. This is a cyclohexane. So I have 1, 2, 3, 4, 5, 6, 7 carbons here. 1, 2, 3, 4, 5, 6, 7, 8 carbons here. These are not related. I don't even have to name them. So that's where counting your carbons first is going to help. Last one, 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6 carbons. So yes, these are definitely going to be isomers of some type. And then I've got a name. So in this one, longest carbon chain, 1, 2, 3, 4, 5. So this is a pentane with a 2-methyl group sticking off, because I'd start numbering from the bottom. Then looking here, 1, 2, 3, 4, 5. Oh, I can do this. See, here's a pentane as well, and a methyl group sticking off. These are conformational isomers. Okay, so here's a challenge for you. What I want you to do is I want you to draw and name the structures of just 3 structural isomers. There's more than that, I promise, but you just want to draw 3, okay? And you'll know they're structural isomers by naming them. That's kind of actually really useful if you're trying to do them specifically, because sometimes you might draw what you think is a structural isomer and you just really drew it upside down, or you drew it with a bend in it and it's actually a conformational isomer. So C6H14. So when I look at this, one of the things that you might notice is that you have twice as many hydrogens plus 2. So 6 times 2 is 12, which is those hydrogens above and below, and then those on the ends. So that tells me that this is a alkane, that these are all single bonds. It's not a ring structure. So in this one, first thing I would do, obviously, is just put 6 carbons in a row. So you see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So there's 14 hydrogens there. So ways that you can make structural isomers is you could move a carbon and hang it off of one of the center ones. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So there, all those dashes would be hydrogen. Another option you could do is you could hang more of them off. So I could put and hang another methyl group. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So see how those would all be different? Top one would be hexane. Next one would be 2-methyl pentane. Next one would be 2,3-dimethyl butane. Okay, all possibilities. You could go back and you could actually attach them so they were sticking off of the same, and you could form a couple more isomers that way. But you can see that there's different ways to link them together, and that's really one of the kind of amazing things about carbon and how come you can have all these molecules in organic chemistry. Last thing we talked about was chiral carbons. Remember that this means that you're looking at each carbon in the molecule. You're looking for a molecule or carbons that have 4 single bonds and all the groups different. And I'm not just talking about the atom bonded next to the carbon. It's everything to the left of the carbon, right of the carbon, above and below. They all have to differ. So in going across, first one, you cross this one off because it's got a double bond. This next one, this one. So if I went here, 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 and here, yes. Can you see that all 4 of those groups are different? So yes. Next one, change colors so you can see them. So next one, this group, this group, this group, and this group over here. Yes, this would be chiral. Next carbon would be a no. And it's a no because I have 2 hydrogens, so I don't even have to try circling things. Next carbon, I have 2 chlorines, so that would be a no. So that one, total number of carbons in that molecule would be 2. Looking at the one underneath, first carbon I come to, no. It's got 3 hydrogens. Second one I come to, this carbon has a hydrogen above, a CH3 below, a CH3 to the left, so no. These are the same hanging groups. This carbon, no, because it has a double bond. This carbon, no, because it has 2 hydrogens. So there's actually no chiral carbons, even though that's a relatively complicated looking little molecule. It doesn't have any chiral carbons because they don't have those criteria. So coming down this last one, starting at the top, I have fluorine, hydrogen, chlorine, and this whole thing. So can you see those are all different? Yes. Second one in the list, this one I have an NH2, I have a C, I have a carbon with a fluorine and a chlorine, and I have this big group down here. Yes, that is considered chiral. Next one, no, that's not because of the double bond. Next one, here I have an OH, I have an H, I have a single carbon group, and I have a big group above. Yes. And then looking at the last one, I have 2 hydrogens, that's a no. So in this one, I actually have 3. This one has 2 total, this one has 0. So I hope that helped. Make sure that you do the homework, the post-lecture homeworks for those. For chapter 4, you can skip functional groups. You can skip any questions about lipids. We will talk about them as we cover them in chapters 5, 6, 7, and 8. We will cover that information, but we won't cover it in this chapter specifically.